Good. Hi, everyone. So let's keep moving. Um, okay, so we've talked a bit about um, scientific method and kind of the idea phase, the literature review phase, hypothesis phase. Now let's get into the actual designs of research and the different options you have there. So when it comes to psychology research, really in any field, there's two main branches of research design: correlational research, and there's experimental research. Experimental research is when you actually place people in conditions or groups and change a variable, and you look and see, does that cause a change in another variable? With correlational research, you're not doing that. You're just looking at pre-existing association, potential association between two variables. You're not changing anything yourself. You're just looking based on available data. Um, is there some sort of relationship? Experimentally, you're actually changing something yourself and seeing, does that change another thing? So there's very different conclusions that we can draw from these two designs. As we're going to see, correlational research does not tell us whether there's actually any causation there. It doesn't tell us whether one variable causes a change in another variable. Experimental research does, at least to some degree, tell us that. And we're going to see why. But this is a really important point. It's going to come up again and again throughout your studies, not just in this class, but in all classes. So it's something you should really pay close attention. Okay, so we're going to kind of start with correlations. We'll move on to um, and kind of talk about why they don't really fit the criteria or satisfy all the conditions we need to infer causation, but how they are still useful. And then we'll talk about actual experiments and why they do satisfy the three criteria we need to infer causation. Okay, so but just before we do that, let's look at a couple examples of correlations. So correlations are just going to be a relationship between two or more variables. So there's kind of some predictive ability there. As one variable changes, the other one will change in a predictable direction. Correlations can be both positive and negative, and we'll talk more about this later, kind of interpreting them. But one variable, a positive correlation means that as one variable goes up, the other variable or multiple variables are going to go up as well. Negative correlation means that as one variable goes up, the other one is going to go down. Okay. So, for example, or several examples of positive correlation would be ice cream sales and shark attacks. Okay, so the more ice cream sold, say, in a city during the week, the more shark attacks on people there are. There's a positive relationship there. As ice cream sales go up, so do shark attacks tend to go up as well. Another one would be height and shoe size. So typically, the taller a person is, the bigger shoe size they wear. Lastly, high school GPA and college GPA. So if you had a high GPA in high school, maybe you're more likely to have a high GPA in college. If you had a low GPA in high school, you're going to more likely have a low GPA in college, and anything in between. An example of a negative correlation, this is again when as one variable goes up, the other one goes down. It would be, say, drinking and GPA. So the more you drink in college, the lower your GPA, or maybe high school too. Okay. So just one other thing to consider, just sort of related to this topic, is when you're measuring variables, whatever your design is, whether it's experimental or correlational, two questions to ask are, whether the measure is valid and whether the measure is reliable. And these are two different things. So a valid measure, the question there is whether is it actually measuring what you think it's measuring. So are you getting at the construct you're actually interested in? An example would be, let's say I'm interested in measuring depression. Well, if I actually measure anxiety instead, then that's obviously not a valid measure. I'm measuring something other than what I'm intending. On the other hand, you have reliability. This is when whether the measure is consistent or not. So let's say someone who is depressed comes in one day and they're, and then they take this measurement, and the next day they're actually just as depressed, not more or less depressed. If you give them the test again, you get the same measurement. That would be reliability. So how consistent is the measure? So if the actual number, the hypothetical number, depression score is not changing, is the scale so not going to change? If it is changing, then it's not super reliable. If it isn't changing, then it is reliable. Okay, so back to this issue of correlational studies. Let's hammer home the point as to why correlation does not equal causality. So there's three conditions that kind of need to be met for you to infer causality, just kind of logical considerations. And if one of these is not met, then you can't really say there's causality. So we'll look at these and then we'll see, okay, which of those two is correlational research missing. So let's say, well, first to think about this question though, I don't mean to overload you, but correlation is what to causality? Opposite, relevant, or necessary? Okay, so just when you're done thinking about that, let's look at these three criteria. So first of all, one criteria you need for inferring causality is temporal sequencing or precedence. So if one thing let's say if one thing doesn't happen before another thing, then it's obvious that that first thing did not cause the other thing, right? If I don't know, poke myself in the eye. No, I don't know why I thought of that example. But if I lean on something and the thing falls over, well, if I leaned on it first before it fell over and then it fell over, that would obviously suggest that leaning on it caused it to fall over. If I leaned on it, a different time, say after it fell over, then obviously leaning on it did not cause it to fall over. The other one is necessary condition for inferring causality is actually correlation or covariation. They mean the same thing. So is a change in one thing associated with a change in another thing? For example, if you flick a light switch, is that associated with a change? The light's coming on. When the cause is present, is the effect more likely to also be present? It doesn't have to be a perfect relationship, but it has to be some kind of relationship. So is one variable associated with a change in another variable, or change in one variable associated with change in another variable? Okay. And then another important thing here is that the differences in the size of the cause should be related to differences in the size of the effect. So for example, with this light switch here, the one where you turn it and it gradually turns the lights from off to brightest. If turning it a little bit is related to the lights being a little bit on, and turning it fully is related to the lights being fully on, that would satisfy this covariation. because the difference in the size of the cause, turning the knob here, should be related to differences in the size of the effect. So more turning equals more light. If that's the case, then we've satisfied this covariation. The last one, ruling out other possible explanations. Is there something besides the cause that could be producing the effect? So something else going on, besides what I think is causing the difference, that could be responsible. Okay, so let's look at one more example. Let's say you get a new cat, and you start to have runny nose. At some point, you're having runny nose and watery eyes, so allergy symptoms. Well, is temporal sequencing going on here? It could be, right? Did your symptoms start or get worse after getting the cat? If the symptoms occurred before, it can't only be the cat, or it probably isn't the cat at all. Right? But that's where temporal sequencing is necessary for causation. They have to occur at the same time, or rather, the cause has to occur before the effect. Is your new cat causing your runny nose and watery eyes? So is there a correlation? Is there covariation? Do your symptoms appear or get worse when you're close to the cat? Do your symptoms disappear when you're out of the house? Do your symptoms get worse when you spend more time with the cat, really close to you? That would get back to this idea of strength. A change in the strength of cause should result in a change in the strength of the effect. The closer you are to the cat, you should be getting stronger allergic reaction. The farther away you are from the cat, the weaker or non-existent. You should get weaker or non-existent allergic effects. Okay, so the last one, can you rule out alternative explanations? So did any other change occur the same time you got the cat? Maybe you got a new litter box. Maybe you're allergic to that. Were there any seasonal changes? Were certain plants blooming? People do get seasonal allergies. You just start using a laundry detergent, possibly, right? Those could be other explanations. So one thing I want you to take away from this is that correlation is necessary to causality, but it doesn't tell us that there is causality. So let me say that one more time. Correlation is necessary to causality, but it doesn't show that there is causality. Another way to look at this is that correlation, you can have correlation without causation, but you can't have causation without correlation. Okay? Say that one more time. You can have correlation without causation, but you can't have causation without correlation. Because remember, that's our second requirement. Two variables or two things have to covary. There has to be a relationship there, turning the switch in the light, cat, and the allergies, in order for there to be causation. But that still doesn't tell us that the correlation doesn't tell us that there is causation. Because there could be other explanations, or we don't know, was there temporal sequencing? Okay. Bottom line, correlation is necessary but not sufficient to infer causality. Okay. So let's start with a bit more on correlations, and now talk more about why they don't really satisfy those three conditions. So again, correlation just means that just one variable goes up, the other variable goes up, down, up or down.